Hi there. Due to the trip, I have to miss our meetings on Monday, so I'd like to record the notes for reinforced concrete members, continuing on about the moment resistance. So here we go. From last lecture, we have talked about how do we calculate the moment for a beam. So a quick review here, if I have a beam, has a rectangular shape, I have reinforcement at the bottom, and this is number 9 from your last time notes. And the height of the beam is 24 inches. We already know. And the depth of the beam is 21 inches. You notice that when I say the depth of the beam, which is D, that means from the top fiber to the reinforcement level. Okay, this is so-called depth. And then the 3 inch at the bottom here is called a concrete cover. All right, this is called a concrete cover. Okay, so this is the depth. Okay, so these are the terminologies, and we have talked about the several steps of solving the moment resistance for the reinforcement reinforced section like this. The first step is we have to assume it's under reinforced. Assume under reinforced. Okay, simply saying that the strain in the steel has reached the yield strain. So the stress in the steel reaches the yield strength. Okay, if that's the case, then the tension force equal to the area of the steel multiplied by the yield strength, which gives you the total tension force equal to 3 multiplied by 60 ksi. So 3 inches square multiplied by ksi and give you 180 kips. Now you should already have this in your notes. Okay, and then we compute the compression force. Compute the compression force. All right, so before I move on, let's list the question here. A is trying to find the moment resistance, and B is trying to find the minimum reinforcement area required for the beam. Okay, so this is in sort of A. So first we'll make the assumption that the beam is under reinforced. That means the yield and give you the tension force. Then we try to compute the total compression force. Let's use capital C for compression, and this is equal to a 0.85 F prime C. Remember, this is the Whitney stress block method. A, which is effective compressive zone size. B is the width of the beam. Okay, so this is the B, don't forget. And the B is actually, 14 inches. Okay, so this is the equation. So let's plug in the number 0.85 multiplied by 3. Okay, because F prime C, indeed, here, let me label here F prime C equal to 3 ksi concrete. Okay, then multiplied by A, which I don't know, and then 14 inches of width. So the unit here is ksi multiplied by inch. Okay, so this is the total compression force. Now we need to require compression equal to tension to reach the balance for the section, and that equal to 180 kips. So I can quickly calculate my effective compressive zone, which is 180 divided by 0.85 multiplied by 3 multiplied by 14. Then I got a 5.04 inch of effective compressive zone. Okay. So when that is obtained, A is obtained, we can go back and confirm steel yielded. Confirm that steel has yielded. How do we do that? We simply calculate the strain in the steel, which is epsilon y equal to the yield strength of the steel divided by the modulus of the steel, that equal to 60 ksi, and let me put here Fy equal to 60 ksi, and then this equal to 60 ksi divided by 29,000 ksi, so 60 divided by 29,000, so I got 0.00207. Okay, so let me use a different color here. This is what we call the yield strain. Yield strain. Okay, switch back. All right, once I have my yield strain, I want to calculate my strain distribution along the section. So I'm going to draw the line here, and this is the strain distribution, by the way. So strain diagram on the section, and I have a compressive strain of the concrete when reaching the yielding that equal to 0.003 by the code. And this is small c, which is the compressive zone size, and it's not A, it's small c, and this is the curvature that my section rotates by, and the bottom here is the strain from the steel. Okay, so given that this distance d minus c, and this is c, the total distance is d, because this is where the steel is at, and this is where the concrete is at, then I can use my similar triangle or trigonometry. I have epsilon cu divided by small c equal to epsilon s divided by d minus c, and all of them equal to tangent phi. Okay, then I can obtain my strain in the steel equal to d minus c divided by c multiplied by epsilon cu, which again, this number here is 0.003. Okay, then I can obtain my strain in the steel, which is c. Well, let me take a step back. Okay, now I have this equation here. I want to calculate the strain in the steel, but I still miss my compressive zone C, because small c here equal to beta 1a, where beta 1 is the index, and beta 1 equal to 0.85 for f prime c smaller than 4 ksi. Okay, and I know my a, so c equal to a multiplied by beta 1 equal to 5.04. Sorry, I think I got this equation wrong here. C equals a divided by beta 1 equal to 5.04 divided by 0.85. I have C equal to 5.93 inches. Okay, so once I find my compressive zone, I can compute my strain in the steel epsilon s equal to 21, which is d, minus c, which is 5.93 divided by 5.93, and then multiplied by a 0.003, and I get a 0.0076. Okay, inch per inch. This is the strain in the steel, and apparently this one is much larger than 0.027 equal to the yield strain, so we're okay, and still yielded. Okay, so at this point we have established the condition that steel has yielded. We'll go on to check what is my lever arm. So the lever arm between total compression and total tension now equal to d minus half a, and that is 21 minus 5.04 divided by 2, and I have 18.48 inches. Okay, then once I have the lever arm, I can directly calculate my nominal moment resistance, which equal to a tension force or compression force in this case, because they're equal, multiplied by distance d minus half a. So I have 180 kips multiplied by 18.48 inches. So I have a 3326.4 kips inch. And I divide that by 12, I get 277.2 kips feet. Okay, so at this point we have found my nominal moment resistance. I want to check my minimum reinforcement area. Okay, so second step B, I need to check the AS min. And of course, you can find this in ACI code 9.6.1.2. Okay, 9.6.1.2. So by that equation, AS min equal to the larger of two equations, right? We talked about this. First is 3 square root f prime c b d divided by a fy. Okay, so I bring the numbers in. This is 3 square root of 3,000. This is a multiply sign, just in case you're confused. And this is 14 inches, and multiply 21 inch divided by a 60,000 psi. So this gives you 0.805 inch squared. Now the other equation, 200 multiplied by BD divided by Fy, and gives you a 200 multiplied by 14 multiplied by 21 divided by 60,000. Okay, and this gives you a 0.98 inch squared. Okay, so I compare both of them. I need a larger, okay, put emphasis here. I need a larger one, so naturally I have a 0.98 inch squared governance. Okay, so this is the minimum required reinforcement area. Okay, minimum. So if this is the minimum, what do we really have here? What do we really have here? Provided AS actually equal to 3 multiplied by 1 inch squared, which is much larger than the required, equal to 0.98 inch squared, so we're okay. Okay, so this is a typical process of how we calculate the moment resistance for a typical rectangular section. Okay, so let's quickly review. We assume the steel yielded at failure, and we find out the compression force, and then let equal to tension force and find my effective compressive zone A. Once I find that, I will come back and confirm whether the steel yielded or not. To confirm that, I'll find the yield strength of the steel, which is 0.00207, given a grade 60 steel. Okay, I want you to remember this number because we use it again. And afterwards, I use my strain diagram, okay, to compute my strain in the steel and to make sure that the strain in the steel is larger than the yield strength, which means confirm our assumption to begin with that the steel yielded at failure. Once I have established that, I'll calculate the lever arm, getting the distance between the compression and tension force, and multiply by the tension force to get my nominal moment resistance. In the end, I will check my reinforcement area to see if I satisfy the minimum reinforcement requirement, and then the beam analysis is completed. Okay, the beam analysis is completed. All right, so this is a quick review of how to calculate the moment resistance for a reinforced section. But this is simply just an analysis part. Today, we're going to move on to the design part. So first of all, let's take a look at some objectives. First, we need you guys to be able to describe the different flexural behavior of an RC beam, in terms of strain condition. Okay. Second, we need you to be able to describe the different code definition for strain conditions. So if there's one term I need you to pay attention to in this lecture is the strain condition. Okay, and last but not least, after this, we want you to be able to determine the stress reduction factor phi for flexure. Okay, so these are the objectives of today's lecture. Okay, so how the beam will fail, right? So we talk about this. The beam will go through a elastic stage, cracked elastic stage, basically uncracked, cracked elastic stage, and then still yielded, then failure, right? So it is critical that we want to keep a balance that when the concrete reaches compression failure, the steel yielded at the same time. The steel yielded at the same time. All right. So by this, okay, we will first establish some flexural behavior. Okay. So some of the terminology, okay, under reinforced. We used this term already, haven't explained it so much, so today we're going to explain it. Under reinforced section. Okay, under reinforced section means the reinforcement intention. Okay, be careful. Only the reinforcement intention. Okay, intention zone yields before concrete in compression zone reaches epsilon Cu. Okay, reaches failure basically, epsilon Cu. Okay, that is to say, if I want to have under reinforced section, my steel yielded already when my concrete fails, right? When my concrete fails. Okay, so this is the desirable. Before we move on, I want to put it here. This is the desirable section. Okay, let me clean this E a little bit. Desirable section, desirable design. All right, so we won't utilize the full extent of the material. So we would like to still yield it to reach the maximum strength, and we also want the concrete fail in compression. Okay, at the same time, preferably. Okay, but sometimes we'll put too much reinforcement in it. Then we'll have the over reinforced section. Over reinforced section. So when we have over reinforced section, the reinforcement in the tension zone does not yield. Okay, before concrete in compression zone. Okay, concrete in compression zone reaches the failure strain of epsilon Cu. Okay, epsilon Cu. All right. Now, these two cases, okay, are the extreme case. Okay, so of course this is undesirable. Okay, undesirable. Okay, now there's a cutoff line, or there's a cutoff point between these two cases, and we call it balanced strain condition. Okay, remember we have talked about this term strain condition before. So what is this balanced strain condition? That means tension or tensilely loaded reinforcement reaches yield strain of the steel, of course, epsilon y, at the same time the concrete in compression zone reaches epsilon Cu. Okay, so the strain in the steel reaches the yield strain same time as concrete crushes. So this is called a balanced strain condition. All right, so you can think of it desirable, undesirable, and then the cutoff point. Okay, so these are the basic terminologies we would like you to understand and remember. And then let's recall the code definition of the strain condition. Okay, the code definition of the strain condition. Okay, so recall in the flexural strength requirement design method, which is from the ACI, right? From section 9.5.1. Okay, we says that of the strength reduction factor phi multiplied by the nominal strength Mn, which we calculated from before, has to be greater or equal to the loaded, right? To the loaded strength or to the load, Mu. Okay, of course, Mu here, 3 lines means defined by definition equal to a load factor multiplied by service load. Okay, which simplified as 1.2 dead load MD plus a 1.6 live load. Okay, live load. All right, of course, Mn is the nominal moment strength, and phi is called strength reduction factor. Okay, but we need you guys to know today that phi is actually a variable based on strain in steel. Okay, based on strain in steel. How so? When we have a reinforced section like this, okay, and we might have a 2 rows or 3 rows for that case of reinforcement, and let's just say the center of this reinforcement is at a distance d away from the top fiber. Okay, and then we also define, be careful here, we also define the distance between the top concrete fiber to the last row of reinforcement as dt. Okay, and apparently d is always smaller or equal than dt. Okay, dt. Okay, if we define these geometries, okay, and then let's draw the strain diagram. Okay, strain diagram. Okay. Okay, now I have compression, I have tension, and at the same level of the last row of steel, I have here epsilon T. Okay, at the center of the reinforcement, which is a distance D, I have epsilon S. Okay, these are different. Okay, so epsilon S, strain at the center of gravity CGs of all reinforcement. Epsilon T, strain at the lowest row of reinforcement. And they're different. And I can comfortably say the strain in the center of the group of reinforcement or reinforcement will be smaller or equal than epsilon T. Okay, this corresponds to this. Okay, this corresponds to the depths. Okay, so let me complete this. This is the neutral axis. This is, of course, the concrete crushing strain, and that equal to 0.003. Okay, all right. Now these are the strain diagram, and per ACI 21.2.2. Okay, it basically provides you a nice table. Okay, so here's a table. Okay, here's the table, and I have first row, second row, and here is the code classification. Okay, here is the strain condition. Okay, here is the strength reduction factor. Basically, strength reduction factor phi, okay, will be a dependent variable based on the strain condition. Okay, so when strain at the bottom fiber or at the last row of reinforcement, okay, not S, but epsilon t, I want to emphasize, okay, it's based on epsilon t, is greater or equal than 0.005. Okay, we call this case a tension controlled. Tension controlled. And phi corresponding equal to 0.9. And then if we say epsilon t is epsilon greater than epsilon y and smaller than 0.005, okay, and then phi equal to 0.65 plus 0.25 multiply epsilon t minus epsilon y divided by 0.005 minus epsilon t. Sorry, epsilon y. Okay, and we call this transition. When epsilon t is actually smaller or equal than epsilon y, we call this compression controlled. Okay, in this case, phi equal to 0.65. Phi equal to 0.65. All right, and now let's just say epsilon y is set equal to 0.002 per ACI 21.2.2.2. Okay, now if you take a deeper look at this phi strength reduction factor here, it basically is saying the strength reduction factor is dependent on the strain in the steel, and it's not epsilon s, but it's the last row of steel. Okay, strain on the last row of steel. That is to tell you that if my strain is bigger than 0.005, which is very large and much more than the yield strain, I have a lower strength reduction factor. If I have a strain that is just a hair smaller than the yield strain, which means my steel is now yielded, I have a 0.65. In between, I have a linear interpolation. Okay, to make it easier for you, if I draw a plot and let my phi to be the vertical axis and my strain in the steel epsilon t in the horizontal axis, and let's say this is 0.65 and this is 0.9, okay, and then this is not right. Let me put this down here. So this is actually epsilon y equal to a 0.002, and this is 0.005. So in terms of this equation, what it's saying is that when epsilon t is bigger than 0.05, let me use red, I have a value of 0.9. If it's below epsilon y equal to 0.02, I have a value of 0.65. Okay, what happens in between? I have a linear interpolation. Okay, so this is called tension controlled. This is compression controlled. And this is transition. Okay, that's how we differentiate phi. Okay, that's how we differentiate phi. So you can see that when we do design, we rely on this stress reduction factor, but you cannot simply use a constant. This stress reduction factor is actually dependent on the strain in the steel. Okay, so let's take a look at the example how we apply this stress reduction factor. All right, so example, okay, let's just say from our last example where we have 3 bars, remember, number 9 bars, and we have a depth of 21 inches. Okay, concrete cover 3 inches. Okay, and I have a compressive strain equal to 0.003 at failure. Okay, and then I want to calculate the strain in the steel, which is here. Okay, and this is epsilon s. But fortunately, since I only have 1 row of reinforcement, this epsilon s equal to epsilon t. Okay, and also my compressive zone C here has been calculated already, is equal to 5.93 inches. 5.93 93 inches. Okay, so let's write down something we already know. So the depth D equal to dt. Okay, which means I only have one row. Okay, since one layer of reinforcement. All right, so my strain in the O steel in the center of the O steel equal to the strain in the last layer of the steel, since also one layer of reinforcement. Okay, and last time from previous example, previous calculations, you say we find out epsilon s equal to epsilon t equal to 0.0076, which is bigger than 0.005. So I know my phi equal to a 0.9 and is tension controlled. Tension controlled. Okay, so if I want to do design, I already know my MN. Okay, I want to find out what is my design strength of phi MN equal to 0.9 multiplied by 277.2 cubic feet, and I get a 249.5 cubic feet. Cubic feet. So this number is the design strength. Okay, this is the design strength. All right, so quickly a recap. Today we have shown you that depends on the strain in the steel, we have under reinforced, over reinforced, and balanced strain conditions. Okay, and we know that the stress reduction factor phi is dependent on the strain in the steel. So we goes on and talk about how do we define phi. So we come up with a table, say if the strain in the last layer of the reinforcement, lowest row, or you can say last layer or the bottom layer, okay, regardless what you say it, it is the last row of reinforcement here at the distance dt. Okay, if this strain is bigger than 0.05, we call it tension controlled, and we set phi equal to 0.9. If it's lower than yield strain, we call it 0.65 for reduction factor and compression control. If in between, we do the linear interpolation. Okay, all right. So after that, we calculate the moment based on the analysis we've shown before, and then at the end, we judge the stress reduction factor based on the strain in the steel, and then apply it to calculate the design stress. All right? Okay, we will talk about more when we return on Wednesday.